In this clip on environmental monitoring with sensors, we will overview three general categories of sensors based on the electrical parameter that is altered in the device as the phenomenon changes. Namely, we are going to discuss resistance, inductance, and capacitance-based sensors. Before we proceed with our first sensor type, let's first review voltage dividers, where we consider a resistive circuit where the components R1 and R2 are in series. We know that the current through each of these devices is the same, and that the voltage dropped across each device is proportional to its resistance by Ohm's law. That is, V equals IR, where here's I. And we have V1 here and V2 there, which happens to be equal to V out. By Kirchhoff's loop voltage law, we know that these drop voltages, V1 and V2, sum to the source voltage, specifically Vin. As a result, we have that the source input voltage, that is Vn, is divided across the two resistors proportionally. So, as an example, if the resistance R2 increases, the voltage at the output, V out, will also increase. So specifically, V out is Vn times R2 over R1 plus R2. We'll later show that the voltage divider is an effective circuit to leverage to take a resistance change in a sensor and produce a change in an output voltage. The first category of sensing devices are those whose resistance changes with the parameter of interest. We'll study in more detail in subsequent clips those sensors whose resistance depends on temperature, that is the thermistor, light, the photoresistor, or strain gauges, and resistive networks such as a voltage divider that can be used with these devices. Other resistive sensors include those that respond to, for example, moisture or touch. By now you have covered RC circuits and know that the time constant of this circuit, tau, is equal to R times C. And what that means is that the voltage across this capacitor will initially start at 0 because the switch is open, but once the switch is closed, it will start increasing. So let's say it closes at time t equals 0. The voltage will increase at an exponential rate given by V sub s times 1 minus e to the minus tau. So after time tau, after closing the switch, this voltage here will be approximately 63% of V sub s. And likewise, after reaching steady state, where the voltage across the capacitor is V sub s, you open the switch, the voltage would decay. So, as either R, the resistance of the circuit, or C, the capacitance of the circuit, increases, so will the response time of the circuit, and the longer it will take for this capacitor, the voltage across the capacitor, to reach the source voltage. Furthermore, we know that the low-pass cutoff frequency of this circuit will also be dependent on these component values, that is of R and C, specifically that omega is 1 over RC. So if the input to the circuit were, instead of this DC, a sinusoid of a particular frequency, one will get a different output voltage magnitude depending on what the values of R and C are. For example, for one particular value of R and C, the output voltage might be sinusoidal like that, but as R or C increases depending on the type of change, the output voltage in magnitude would decrease. This type of conditioning circuit can be used not only with resistive-based sensors, but capacitive-based sensors as well. From your study of capacitors, you know that an ideal capacitor can be modeled as two parallel conductive plates of area A that are separated by a dielectric of thickness d. The capacitance can thus be calculated using this equation. If one designs a sensing device in which the distance between the plates is altered with a phenomenon, for example force, then the device's capacitance will also change. One can also design a sensor in which the dielectric constant changes with the phenomenon. This is the principle upon which many humidity sensor designs are based. You may also be familiar with the operation of an ideal transformer, where the transfer of power from one side of the transformer to the other is conserved. However, the voltage at the secondary output is determined by the AC voltage at the input and the relative number of turns between the secondary coil and the primary coil, which is defined as the turns ratio. That is, N is the number of turns in the secondary relative to the number of turns in the primary. If we can design a sensor where the turns ratio changes with the phenomenon of interest, we can see that the voltage at the secondary will also change with that parameter. Coil-based sensing operates under a principle where the parameter of interest changes the coil coupling. For example, in an electric guitar, the moving metallic guitar string influences the coil in the pickup. In an LVDT, a moving magnetic core changes the coupling between a primary and two secondary coils, therefore effectively changing the turns ratio. As a sensor's rod extends, the core moves, say, to the right, thereby increasing the voltage in the right secondary and decreasing it in the left. As the sensor rod gets pushed in, the core moves to the left, thereby increasing the voltage in this secondary coil, but decreasing it in that coil. The remainder of this module will detail the following three resistive-based devices: thermistors, photoresistors, and strain gauges. These are just three common sensors used by not only electrical engineers, but also mechanical, civil, biomedical, and environmental engineers for a wide variety of applications.